Now I'll go into detail and talk about this kind of architecture we use as building blocks when we build different types of neural network models. And here comes a little bit of overview of the course. So today I'm going to talk about feed-forward neural networks. Next week we'll talk about convolutional neural networks that are very well suited for images and also specific kind of as feature extractors in sequences. And then in week 3 we'll talk about recurrent neural networks, and autoencoders is a type of model that is very well suited for unsupervised learning. We'll talk about that in week 5. Yes, and then week 4 is on tricks of the trade. There we'll learn how to kind of use these models better to get better performance. And in week 6 we'll talk about reinforcement learning, and reinforcement learning can kind of use all these types of models as kind of ingredient, as building blocks. Okay, so about the feed-forward neural network. So here we imagine that we are doing supervised learning. So in supervised learning we have both an input and we have an output. And what we do in the neural network is that we train a conditional model. So that means that we are given an input and then we want to predict the output. And the output can be, for example, in regression, it will be continuous values we want to predict. We'll mostly focus on classification, where we want to predict what class does this input belong to. So you can imagine that you have this d-dimensional input of all the x's. That could be an image that we have kind of made into a vector by kind of unfolding all kind of the 2 dimensions to a 1-dimensional long vector. And what the neural network does is that it actually has inside, this is a simple neural network with one hidden layer. So each of the units in the hidden layers, you can see there are m of those, acts as a linear model. So that means that it takes all the inputs and it takes a weight. It weights each of the inputs. If this weight is large, then it means that this specific dimension is weighted more. And then in the end you have these m. So you get one input vector in, and then you get like one hidden unit representation. Then you apply a non-linearity, a so-called activation function to this non-linearity, and then you repeat this process again with a second layer of new weights, and then in the end you compute the outputs. And I'll be more specific about how you actually compute the output. But in each of the layers, both the hidden and the output layer, you apply some non-linear transformation, or you can also apply the identity. And the last thing here to note is, just for notational convenience, that we introduce this extra 0th input. This acts as like the intercept or the bias term we know from statistical models. So here in the next slide I have written out with symbols what I mean here. As you can see, the kind of to compute the input to the jth hidden unit, we have this sum over the weights in the first layer that we multiply with the input, and then we add this 0th component, which is the intercept, and we can then write this compact as a summation from the 0th dimension, the bias summation, to the dth summation, and then always the 0th input is clamped to 1. And then the complete output of the network, which I call H2 in this case because we have 2 layers, is just these kind of linear models, activation functions, linear models on the activated signal, and then some activation function F2 in the end. Yes, so a little bit about these activation functions. So there are different options. If we, for example, are working with binary classification, so that means we want to have a system that can say whether it's one class or another class. It could be whether a patient, we make a blood test and then we use that as an input to our model, and then we can predict whether this patient has a disease or not. Then we can actually use a logistic function, because that takes a real valued number and then transform that to a number between 0 and 1, and we can interpret this as the probability of a positive from the test. And then the probability for the negative is 1 minus this number. Another activation function we can use is a hyperbolic tangent. So that is illustrated with the blue line in the plot, and that is has again an input is defined on the real axis, and then the output is from -1 to 1 in a monotonic way as shown here. It actually was very popular as kind of activation function for the hidden units in a neural network for many years, but because of this saturation out in the ends, it means that when you do gradient descent based learning, then you can actually get that the learning process gets stuck even though your output is incorrect. And that means that it can be prone to, if you're not careful, it can be prone to be fit, even though kind of be thick, what's the word I'm looking for? Get stuck even though you have not learned the training set yet. So people instead have started using this, what is called the rectified linear unit. So that is this ReLU, and this is just a max of 0 and the input argument, and that is the yellow line. So it's kind of flat 0 when the argument is below 0, and then it's a linear when you are above. And that actually has both kind of implementation in the code is fast, and also it has better convergence properties. So that has become quite popular to use that.